Hey, I'm at my brand new microphone because the audio was terrible on the other one. So I wish it was a clip-on microphone. This would be a giant clip-on microphone. But uh, this is very inconvenient. All right. So uh, remember, being able to identify graphs and determine the order from graphs. We've been spending a lot of time on looking at that one that said natural log of the concentration versus time is going to give you a straight line. So if you see something like that, a straight line, and you want to get the rate constant, that's the negative slope of that line. Okay, that is one. Now, I've been giving a little bit of short attention to no attention to second order reactions. I just want to mention, okay, now first of all, let's keep this in the back of your mind. If a reaction is zero order, rate is equal to K times the concentration to the zero power, right? That means that if I change my concentration, that's going to have no effect on the rate because anything raised to the zero power is 1, right? Except 0. 0 to the zero power is not 1. But so your rate then is just going to be equal to your rate constant at that point. So let's take a look really quickly at second order reactions. Second order reactions, I'm going to give you a very brief mathematical interlude. We could say that the rate is equal to that. It's also equal to negative. I'm just going to leave the brackets out for the sake of making it look a little cleaner. Now remember, this represents the concentration of A. I'm just leaving it out so that we don't have to worry about brackets. So what we have here is we have another sort of a differential equation, and I just want to go through it quickly with you to show you where the result comes from. And next year, once again, you will be learning about these types of equations. So this is a change in the concentration of A with time. Remember, it's negative because we have A turning into something else, so we have to have that negative sign. Now, if we take this and we once again separate our variables, I can say, well, negative dA, that's that infinitesimal change of A concentration, divided by A squared is going to be equal to K dt. Okay? Now, this is a very special form of, uh, of, of a differential that we're going to integrate. Now, again, that's the opposite. So I make a little symbol there and a little symbol there, and this tells us to do a certain mathematical function. Uh, I'm just going to go ahead and show you what we end up with for the result. By the way, if I took this function, 1 over x squared dx, and I did this thing called integration to it, the way integration works, let me just give you a brief interlude. I could write this as x to the minus 2 dx. Now this symbol tells us to do something to this function. It tells us to add 1 to the exponent and then divide by the brand new number that you get. So looking at this, if I add 1 to x to the minus 2, it becomes x to the minus 1. Right? And I divide it by minus 1, which is the same as that. So basically, that's what you're going to get when you do this thing called integration. And you get some constant, but that's for next year. So we're going to do the same thing here. We can say, whoa, I'm going to look at this process of integrating between A at time 0 and A at time t. So what you end up with is you end up with this. This is going to be 1 over A, I'll put the brackets back here, at time t, minus 1 over A at time 0 is equal to kt. So that's the result you're getting, and I'm sure that my computer's blocking it. So let me rewrite it over here. So when we do this math, we come up with 1 over A at some time t minus 1 over A 0 is equal to kt. And one of the ways that we can write this is let's write it like a line. because that A0, that's going to be a number that's not going to change. That's what we start with. So we say 1 over A at time t is equal to kt minus 1 over A0. Okay, so hopefully this is going to look a little bit, let me see if I get my thing here. Hopefully this looks a little bit like y equals mx plus b. So if we were to plot, I'll move back over here. I need like a cameraman, whole crew. So if we were going to plot 1 over, then the marker's dying, 1 over the concentration of A versus time, we should get a straight line with a positive slope. This indicates second order reaction, okay? And second order reaction is the slope of this line is going to give you your rate constant K. So when you look at your sheet here, they have a couple of them where they say, hey, let's identify things. So take a look here. Let's take a look, if you have this sheet, at questions 8, 9, and 10, just to go ahead and look at them. So 8 says, the decomposition of an unknown molecule was found to be first order. So they show you something like this, and they say, fill in the unit on the vertical axis. This is time. So what do we know about first order? What do we put on that axis? ln, yeah, ln of whatever. Or no, not times 0. Ln of concentration. Natural log. Beautiful. Now, what is the unit of rate constant? Well, it's going to be well, the natural log doesn't have a unit on it, so it's just going to be per second. And you could show that. You could say what's the unit for a first order? Rate is equal to K times the concentration, and this is molarity per second. And this is molarity. If I want the unit on that, I just divide both sides by molarity. Bless you. And so my unit is just second to the minus 1. Alrighty, so that's good. So let's take a look at question number 9. It says C5H6 reacts with itself. It dimerizes to form C10H12 according to the following process, and they give you the reaction. And they say 3 graphs were shown below and were constructed using data pertaining to the concentration over time. The data was collected during an experiment in which pure C5H6 was mixed with distilled water where it reacted to produce C10H12. Remember, we are looking for straight lines, and we're looking for what's on the vertical axis. So if I plot in A, log versus time, I don't have a straight line. I have a curve. So it's not that one. If I plot concentration versus time, I don't get a straight line. So it's not that one. That would be a zero order reaction. Finally, if I plot 1 over C5H6 versus time, I get a straight line. So what order is the reaction? Bravo, bravo. Good job. Okay, and then all the other things, you just look at the graph. Now, for example, they say, what is the rate law for the overall reaction? We can write that because we know how to write rate laws for second order reaction. Because if you look at the reciprocal, now they write it as this, C5H6 to the minus 1. That means the same as that. So if I see 1 over that concentration versus time and I get a straight line, that indicates second order. Okay. So remember, If it's natural log versus time, I get a negative slope. That's first order. And if it's just concentration versus time, and you see a line for that, that is a zero order reaction. Okay, so then we would be able to say, since we know that this is second order, rate is just equal to K times the concentration C5H6 squared. So that'd be your rate law. And then they want you to calculate K. So you'd have to kind of go back and estimate a slope off of this. And if you're not, if Dryden gets a slightly different answer than Jillian, it doesn't matter because it's tough to try to estimate the slope. You should be in the same ballpark though. So, and it says calculate the concentration of C5H6 when 250 seconds have passed. At that point, you'd have to go ahead and if 250 seconds have passed, since you are going to be able to know the rate constant, let me see here. How can we go ahead and do that one? Because we would have to basically look at the slope of that line, set it up like a y is equal to mx plus b problem, and since we have the time here, we would be able to go ahead and calculate the amount left after that certain amount of time. I'm not going to put that on a test though. I will ask you to recognize graphs, okay? And I will ask you to do calculations based around first order reactions because they're probably the easiest. It's kind of slope, maybe, but if I have you find a slope, probably not. I'm probably just going to say there's only so many things I can ask in 42 minutes. So, basically it's going to be identifying first and second order reactions, looking at graphs, doing these kinds of problems where we use experimental data, right? Definitely a question like question number 1 would be on there. And that's really, and some half-life stuff. So let's take some time and look at half-life stuff. And that's pretty easy. I'd probably stick with first order. It's pretty interesting because if you want to, for half-life, T1 half for a first order reaction is equal to the natural log of 2 divided by your rate constant K. So you can get that value of half-life, and then we could use several different methods to calculate how much is left. If we have an even number of half-lives, it's just going to be the amount left at time t is equal to the amount or concentration we start with times 1/2 to the number of half-lives. And that's usually going to be time divided by half-lives. So you can certainly use that equation. Or you could just say, if I have an even number of half-lives, like let's say the half-life is 8 days for iodine 127, and I say we start out with 100 grams, and the half-life is 8 days, how many grams will be left after 64 days? Well, I've gone through how many half-lives? Yeah, and so you just have to say, well, after 1, it's going to be 50. After 2, it's going to be 25. And you could do it pictorially as well. Just draw it out and calculate it that way. That's probably the easiest way if you have an even number of half-lives. If you don't, you could either use that, and like I said, the other one is the amount I have at time t is equal to my starting amount times e to the negative kt. So if you don't know, if you just have time, but you're able to get that constant, you can use this equation as well. Yeah, 12. Take a look at 12 and 13. Let's do those now. Oh, before we do that though, let me just tell you a little bit about how do we get half-life equations for a second order reaction. And I want to show you something that's kind of interesting. Let's take this version here, 1 over A at time t is equal to kt minus 1 over a0. Now, what's interesting is to solve this for half-life, well, my concentration here would be half of what the concentration is here. So I'd have 1 over 1/2 a0 is going to be equal to kt minus 1 over a0. So if I go ahead and calculate this, switch it around, I'm going to have 2 over a0 minus 1 over a0 is equal to k times the t1/2. So 2 minus 1, so I have 1 over my initial concentration, that should be the bracket, is equal to k times the half-life. Again, I'm running out of space here. So let me write up here the expression for half-life then, for a second order reaction, is going to be 1 over k times a0. So what's interesting is the half-life for a second order reaction depends upon how much you start with, whereas a half-life for a first order doesn't depend upon what you start with. Again, I'm not going to ask you this, but I want you to know it. I want you to take it with you when you leave Elk Lake. All right, so let's concentrate then on questions 12 and 13. And those are, and again, this is all being recorded, so you'll have a chance to watch this if you ever want to. So it says a 1.0 times 10 to the mole sample of a compound that undergoes first order process is known to have a half-life of 15 minutes. So 1 times 10 to the 2 is 100. So we're starting out with 100 moles, and it says it has a half-life, T1/2, is equal to 15 minutes. So it says how long after 45 minutes? That's 3 half-lives. So we're going to have 100, it's going to go to 50, so that's 1 half-life, and this is mole. And then after 2 half-lives, I'm going to have 25 moles, and after 3 half-lives, I'm going to have 12.5 moles. What's that? Take 45 and divide it by 15. Okay. Now, let's say I have this same question, okay? And this same question, I say, how much is left after 87 minutes? Well, that's not an even multiple of 87 minutes is not an even multiple of half-lives. So how would we do a question like that? I guarantee you I'm going to put one on that's like this. So let's take a look. Let's do the same problem. And please pay attention, because this is a good one. We're going to have 100 moles, and the half-life is still 15 minutes. And I say 100 moles of A, and I say how many moles left after 87 minutes. Thinking, well, I could divide 87 by 15, and I'm going to get some fractional amount. So here's what we do. We can go ahead and do this one of two ways. Either way is fine. The first thing is, let's solve for the rate constant, so then we can use our exponential equation. The rate constant, k, is equal to the natural log of 2, which is 0.693. Is it? What is the natural log of 2? 0.693, right? Calculator validating. Yeah, 0.693. Over 15. So my k value is going to be 0.693 divided by 15, and that's going to be 0.0462 per minute. Now, the amount I have at time t is equal to my initial amount, 100 moles, times e to the negative k, 0.0462 per minute, times 87 minutes. So now we're going to go ahead and do that. Yep, because it's k times t, e to the negative k times t. Yep, that's okay. So let's go ahead and do that. We'll multiply through times 87. And I'm going to raise e to that power. And I'm going to times it by 100. And I get 1.79 moles are left over. Now let's do it another way. Maybe you don't like playing around with these exponents. No? Let's try it this way. My number, or my amount at time t, is equal to my initial amount times 1/2 to the time divided by the half-life. So 87 divided by 15, so 100, raised to 87 divided by 15, that's 5.8. And let's go ahead and see if we get the same answer. And you get exactly 1.79 moles. So you have two ways to do that problem. You might find that one to be a little easier. Half-lives. So that's basically everything. So if you think about it, we've got the relative rates to compare. You know, if I have a reaction, I can compare the rate of disappearance of one to the rate of appearance of another, or whatnot. We have these experimental types of deals here where we have to figure out the order and the rate constant and the unit on the rate constant. We have a discussion of graphs and how we can look at graphs and get orders of reaction and information from graphs. And we also have this idea about half-life. So that's really going to be the whole gist of it. Before we wrap for today, I know I've been talking for a long time and this is going to be a long video, but there are some things I didn't get to tell you, and this is a little bit too late to put on the test, but I do want you to have it in your notes, because someday you might need to take this notebook to university and refer to it. I told you that there's something called activation energy. And I could have A plus B over here, and we have to have some activation energy to get past that hump to get our product C plus D. Now, we can get a lot of information from an activation energy diagram. But you might want to say, well, hey, what is this activation energy? How do we get that activation energy? And what does it mean if my energy at the end is lower than the energy when I start? Remember, this axis here is energy. And this axis here is what we call reaction progress. Now, this is a cute little thing to know, a very useful thing. If my products are at lower energy than my reactants, that's an exothermic reaction. If I go ahead and say, okay, look at this energy difference here. It's negative, so my delta H would be negative for that reaction. It would be exothermic. If I had a reaction and you saw something like this, where I have a different thing. I've got two chemicals here reacting to form products, and now the products are at a higher energy than the reactants. That's an endothermic reaction. But what I want to bring home to you is, and again, this will not be on the test, but I just want you to walk away knowing it. There's an equation called the Arrhenius equation. The Arrhenius equation enables us to get values for the actual values for activation energy. Rate constants we learned by looking at graphs and doing experiments. We could solve for the values of K. So if we do an experiment at two different temperatures, we have a really great little equation. The natural log of the rate constant at temperature 2 divided by the rate constant at temperature 1, carrying it at two different temperatures, is equal to the activation energy over R times 1 over T1 minus 1 over T2. So these are your Kelvin temperatures, and that's R 8.314 joules per mole per Kelvin. So if you needed to, and you won't for this class, I'm not going to have you do it, but if you needed to, you could get an actual value for activation. That's all I have to say. Do you guys have questions for me? You want me to post a little practice, 3 or 4 practice problems online for you to try tonight with explanations? Okay.
So it's only.
Here, I'll write it all down so we're all on the same.
Number one.
We're gonna have a problem like number 1. One like number 1. That's
4, 5, and 6.
Wait. Let me see here. Be able also to look at number 2 and get some information about those slopes of the tangent line. So number 1, number 2, and then questions like 4, 5, and 6. I'm not going to put 3 of them on there. I'll put 1 of them on there. That's fine. And then half-lives, like 12 and 13, and identifying graphs. Identifying order through graphs. Now remember, if I talk about the order, we talk about the order with respect to each reactant, and then the overall order. That overall order is going to be m plus n. So if I have a first order with respect to A, first order with respect to B, the overall order is second order. You guys can do it. I have faith and confidence in you. Okay.